We got the screen now. So
yeah, it'll be
something?
delayed a little bit.
Okay, there we go. You're streaming. Cool.
We're not seeing anything yet.
There's a delay on it, guys.
There might be a small delay on it.
I see Corey on the floor.
It's buffering. Interesting.
That might also be me.
Oh, it does say dropped frames is 88%.
Why?
Because we have terrible connection.
In the middle of the desert?
To the internet?
Properties. Preset. Yeah, we're doing 7. Yeah, we're outputting in 720p. Right? Can you check that on the stream wheel? We're outputting in 720p, right?
Let me see.
Might switch us to 480. That might be the smartest play here.
I got 480.
It's 480 right now.
Yeah.
That's fine. All right.
If you have like an internet connection I can use real quick to figure out how to change. I just need to do something.
Go for it.
Can you find a way to mute the microphone when you don't want to talk? Alright, I need to leave. Let me know if you guys have any questions.
Testing.
All right, there we go. Now we're in on the new mic. So the audio quality should be a bit better.
Okay. Now mute it.
Now we're...
I didn't see it.
Now we're...
I don't get iPhones.
Huh?
I don't get iPhones. It's searching, right?
Yeah. There we go. Now we still got audio coming through. Device, USB digital audio. We're golden.
You have live image right now, right?
Yeah, we do. We do.
Hey, we just lost it. No, just kidding. So YouTube is not receiving enough video from the capture card or from the computer?
No,
or
it's
just
because of connection. We literally just aren't beaming enough signal width right now. Does anyone have like really good internet out here?
I don't think so.
Does anyone have AT&T?
Nope.
Maybe. Oh, okay. We're back now. Hey, Corey, does your camera have an auto shut-off procedure?
Auto shut off? Yeah. Like after a certain amount of time. I just turned off. They like the live view.
It seems like this size is a good size. Oh no.
Whoa. Thanks, Corey. Although the battery is going to run out a few times, I wish I knew they had ports here because I could just plug it in and be good to go. I only have 5 batteries. So I don't know how long we're doing this live view or whatever, but I'm going to turn it off until we start.
We're running right now. Yeah, we're streaming right now. We might just not...
Wait for the best.
Yeah. How long do you give us in terms of total live stream time, do you think, across all those batteries?
Zachy, I'm going to
What?
say
What?
between 45 minutes and 2.5 hours.
That's golden. That's
Maybe
golden.
on 15. He's throwing a 15.
You want me on 15?
I'm going to turn the brightness down.
15? 15? Copy.
Be careful with language and people that are around you. We already got a text from a mom that there's stuff that so be careful with that. Stay on channel 15.
Hello, everybody that is joining us. We are currently filling our liquid oxygen tank. We have pre-chilled with liquid nitrogen to bring the tanks to a cooler temperature. This way, we don't lose as much liquid oxygen as without.
And we don't run the danger of cryoshocking any components. But
Exactly.
before we get into that, first off, we'd like to thank everybody who's viewing right now. We apologize for the connectivity issues. Our cell service is not the greatest out here. We assured you the hardware is doing just fine.
Mm-hmm.
It's just we're trying to settle out our connectivity. It seems like it's a little bit better right now, but we'll see as the stream progresses. I'm Shrey Patel,
I'm Zaki Saibzada.
and we're gonna be your co-hosts for this stream today. If you guys aren't aware, we're UCI Rocket Project, and we're going to be doing a hot fire test of our freshly developed methylox engine,
Yes.
running on liquid natural gas and liquid oxygen. Zach, do you want to tell us a little bit about what's kind of taken to get here,
It's
time
been
process-wise?
It's been a long journey. This engine has been roughly 3 years in development. Last year we attempted to perform our first static test fire, and it went pretty well initially, and then we ran into a couple issues, and we have since attempted to improve. So what you're looking at right now is the cold brew test stand. We developed it after our first SGF to minimize the time it takes to perform
Set up on site.
To set up on site.
The issue with trying to perform a test fire is you need to leak test all of your components prior to the actual ignition of the rocket. And if you're going to be assembling your rocket on site, that means you got to test as you go. Versus if you have a test cart like we do, we actually just we put that on using a forklift. We put that into the bed of a U-Haul, and then transported it out here to the Mojave Desert, where we forklifted it off and then bolted it onto the I-beam. So it actually shortened our development process for getting everything ready here on site by quite a bit. And so what you guys are seeing right now is the fill for our liquid oxygen. You can see two big dewars. Those would be the giant silver hydro flasks that you guys are kind of seeing on the concrete stand right there. And in between them, you can kind of see looks like a silvery cylinder, and that would be the engine. And the little black tip on there is going to be the nozzle, and that's where you're going to see the ignition come out here in a second.
Exactly, and you can see on the stream we have our chief engineer Chris Hickey Anderson.
Yes.
Yeah. He is operating our dewars, filling the propellant tanks right now.
And so part of the reason why we have so few people on the test stand right now, and part of the reason why we're being so careful and methodical with this whole process, is these are cryogenically cooled liquids. And so oxygen is not normally a liquid.
Mm-hmm.
You have to chill it quite a bit to get it into a liquid state. And same goes for natural gas.
Exactly.
And so in doing so, you're able to chill them down to liquid temperatures and use them in a rocket engine. Reason being that a liquid's a lot more dense than a gas, so you can fit a lot more into your tanks if you run it as a liquid versus if you run it as a gas.
Exactly.
That's pretty cool. So there's going to be a test for another rocket going here in a moment, but so as you can see right now, we're hearing ignition of another rocket off on the other side of the test site. That would be the noise you guys just heard. It's a 3-stage solid rocket.
So there is an initial booster phase that brings up to high altitude and high velocity, and then after that it ignites a second stage, in which it again moves it even further at a again higher velocity.
Right.
And then the final stage is what pushes it to its absolute limit. We're gonna
This is how a liquid or a solid rocket in real life would behave.
exactly
Because the reason why you want stages is because you can reduce the mass of the rocket, which makes it easier to accelerate it further.
exactly.
So if you have a very, very large initial kick from a very big first stage, which would be what most rockets today use a huge first stage, and then you're moving at an extremely fast velocity. If you dump that stage and you ignite a second portion, which would basically be like a rocket within the rocket,
Exactly.
to put it simply, you'd already be going the speed that you're going at, but now when you accelerate, you'll accelerate much quicker because you have a lot less mass that you're carrying with you.
So we are currently at we're very close to finishing our LOX filling.
And once that's complete, we can move on to natural gas.
Exactly. So the reason we use natural gas is because our engine, like Shrey said earlier, it is a liquid oxygen, liquid methane engine. However, you cannot source pure liquid methane. And
It's incredibly difficult to do so. So we use natural gas, which is a very, very close approximation. And here we're getting some close-ups of the engine here in a moment, and at what the test stand crew is doing at the cold brew. And so it seems that LOX is fully complete, and now we can move to liquid natural gas.
They are currently detaching the liquid oxygen hose from the dewar to our test stand.
I suppose we should explain why we're doing what we're doing, kind of from a fluid system perspective.
Okay.
And so we have a cart, and what this cart effectively does is it has a series of valves and of different kinds. You have manual valves, ball valves that a human would operate. You have solenoid valves, and what all of these do is create starting and stopping points for the fluid flow as it moves through the cart. Because if you just blasted out the propellant straight out the back, that's really dangerous, and there's a lot of room for failure there. And there isn't a lot of control that you can exert over the system. And so in doing this, by having valves that are in progression back and forth with one another, you can effectively allow us to monitor the system on a step-by-step state. So what we have is valves and pressure transducers that tell us the pressure at different steps within the system. And then we also have, and then you also have thermocouples, which measure the temperature at different stations inside of the test stand. So I've got the question from the chat of when are we going to start the test. So we actually just finished filling liquid oxygen, so we're about halfway to just the fill stage. And once that's complete and all the initial checks are ready and good to go, we'll be actually ready to fire here. We're actually really close to firing. We have a test procedure in front of us that we can kind of read off incrementally as these stages go on.
So they should be moving on. We are currently removing the liquid oxygen dewar from the test stand. This way we don't have large amounts of propellants at the same place at the same time.
Because these are after all rocket propellants. They're highly energetic and could easily ignite if not taken care of correctly. Exactly. So we got to make sure that we kind of do everything in steps. And so we have just received word that the LNG side is pre-chilled. So we are good to go on filling as soon as this oxygen dewar is taken away. Exactly. And you can see that it's kind of moving away on the forklift now.
Mm-hmm. We will have a truck come by with our liquefied natural gas, and then they'll begin the filling process from there.
How big is the rocket itself? So we actually are just testing the engine today.
Yes.
But the engine would be about, if you include the combustion chamber and nozzle, that would be about 3 feet in length. Maybe a little bit shorter than that.
Combustion chamber. I believe that's correct. A little shorter than 3 feet.
But the overall rocket is 16?
We're actually working on reducing the length of the rocket. As of last year, our initial estimates were like 22-ish feet from
Tip to tip.
from nose to tail. We have since been able to reduce that by roughly 4 to 5 feet. So we are hopefully looking at a 13-foot rocket, with all things considered in the end. Any other questions? So as you can see, that truck right there houses our LNG doer. So they're gonna pull in a little closer very soon, and then from there we will begin filling with our LNG. And some of you, if you're joining us from our previous attempt at STF2, we did
STF for reference means static test fire.
Yes, thank you.
There's different ways to test a rocket engine. You have STF, which would be a static test fire. You have a VTF, which would be a vertical test fire, where you have the rocket engine turned upwards. And effectively in a VTF, you're just clamping down the rocket and it's ready to fire. And you're testing everything as if it were to fly, but you're just holding it just so that.
Exactly.
You also have cold flows, which we've been doing for weeks now leading up to this, where you chill the system as if you were to run propellants through it, but then you flow something that's inert, like nitrogen gas or helium gas, so that way you can basically simulate what the system looks like. It's good for pressure leak checks, because all of these fittings are hand assembled. We don't have machines assembling these fittings for us, so we need to make sure that there's no leakages between any of them. We need to make sure there's a good amount of tape between the NPT fittings on the cart, and we need to make sure that the compression fittings aren't cross-threaded, leading to some leakage out. And so as a result, there's a lot of different kind of tests that go through before we can actually move forward with something like this. Other ones would include an actuation test, where you set up all the electronics, because all these valves are for the most part electronically controlled, and we'll cycle them back and forth using our control box for our avionics systems.
You guys got a countdown?
So,
Plus minus.
Just a moment, we're having some changes in the camera settings so that way we can kind of improve the feed. We've got a really good question in the chat. How much thrust does this puppy have? So that's a bit of a tough question.
Yes, we have had, we've only performed one truly successful static test fire, and that was at static test fire number 1. Our initial calculations came out to be roughly either 1,300 pounds of thrust or 950 pounds of thrust. The reason for this sort of variance or like uncertainty is because
there were some design changes that we had to make.
Yes, we performed design changes. In addition to that, some of the documentation from years past has like disappeared into the cracks and creases.
of time, basically.
Exactly.
Oh no, we
So-
lost feed.
What?
Yeah, we're at 0 kilobits.
It's student espionage. Corporate illegal.
typical at university.
All right, we're back. And so our target thrust for right now is about 750 to 800 pounds would be a pretty solid number.
Right. So our first static test fire, we found that the engine was able to produce roughly 750 pounds of thrust. However, we have since done, like Trey said, some design changes.
Including changing the combustion chamber length
Yes.
and a lot of changes to the valves and the pressure level that we operate the tanks at.
Exactly. So with all those changes performed, we should be looking at a higher thrust. We are aiming for 1,000 plus, but we'll definitely see, and we'll keep everyone updated as we move along.
Is it regeneratively cooled? It is not. So the engine that we are developing for the future will be regeneratively cooled.
Yes.
But for this one, it is ablatively cooled with a phenolic tubing on the inside. There we go. We had a rocky connection there for a moment. Apologies, but we actually don't have our C-star target on hand, but we do have an expected ISP of about 200. And for those of us who are tuning in and who aren't familiar with what ISP means, ISP is a good measure of effectively the fuel economy of the engine. It's how much thrust does it develop per kilogram of propellant burned.
So as you guys can see on the stream right now, they are currently filling the liquefied natural gas. That's what you see, a hose connecting to the truck bed. From there, it's probably about 10 to 15 minutes away from a
An ignition.
combustion. Who do you want to interview?
Do we want to interview Wes? Since we're doing crop stuff right now.
Should we just not do an interview?
We're supposed to do this video. Wes, do you want to do an interview real quick?
Yeah.
Pull up a chair. So at this time, we're going to be inviting over one of our current propulsion leads, Wes Hellwig, for a quick interview. You can actually sit right in the middle here. That way you're closer to the mic. Not numbers, just like general questions. So just kind of like an introduction, Wes. Introduce yourself.
Hello, everyone. My name is Wes Helwig. I'm a senior at UCI, majoring in aerospace engineering. I'm one of the 2 propulsion leads on the Rocket Project, and I've been on the project since I was a freshman.
Oh, really? You've been on the project since you were a freshman? Dang, dude. No, I thought you were joined when you were a sophomore
Oh,
or
really?
something. Yeah.
No, yeah. Yeah.
So, did you have any part in the design of the cold brew structure?
Yeah, so Chris did the main CAD work, but I did the welding with one of the guys who graduated, Sebastian, who's probably watching.
He is. Seb is watching, yes.
Yeah, we did all the welding, and then I did the painting, and also part of the thrust measurement system fabrication, those big linear rails that you see. And then I also did the first design of the tank weight measurement system that you can't really see it, but those tanks are sitting on load cells. So I did a design project to build that.
So can you explain why there are those large flat plates next to the engine?
Yeah, so those are blast shields. Are you talking about the front plates, Zach?
Yes.
Yeah. Okay. So the front plates, those are blast shields. If the engine happens to explode, that will protect the plumbing and the tanks, so that we don't get larger explosion if shrapnel were to pierce the tanks. And then those plates on the side are just mount panels for plumbing.
Is there any like specific reason for making cold brew into like a very long cart? I guess.
Yeah, I guess talk about like where do all these dimensions kind of derive from?
Like the physical dimensions?
Yeah,
or?
the physical dimensions of the cart itself. Where do they
Well,
kind of
so
come
the
from?
first static test fire we did, we basically brought all of everything out and then assembled it on site, which took all day. So the idea behind cold brew was to have a mobile test stand so that we could basically assemble it in the lab and then just roll it out here and reduce our time from setup to fire.
Oh, we've got some nice shots of some frost on the components. Because all our liquids are so cold, it actually freezes some of the moisture in the air onto the components as the heat gets transferred in, and you can see some frost building up on some of the components here.
Right, those propellants are roughly negative 290 degrees Fahrenheit and negative 260 degrees Fahrenheit.
Yeah, they're pretty cold, and that's why we have so many valves and checkpoints where we can confirm and go no go on the procedure to kind of make sure that we're doing stuff right, making sure that we can keep track of any anomalies as they happen, rather than kind of at the end. And so I'm seeing a question in the chat about what are you guys expecting from this test? So we'd like to see successful ignition of the engine. We'd like to see a good full-length burn as well.
Yeah, so we decided to up. Initially, we were going for a 7.4 second burn, but at the last minute, not last minute, but a couple days ago, we decided to increase our propellant weights in the tanks to try to get a full thrust profile. If you watch the very first static test fire, we kind of had a hard start, and then because we had serious methane boil off, it burned only LOX and the phenolic. That's the ablative liner. So it burned that for a while. So ideally, it'll actually end with a methane only burn instead of a LOX only burn.
And the reason why you typically want to go fuel rich over oxidizer rich is it keeps the temperatures down on the exhaust gases and keeps you from melting or blowing apart anything.
And you can also increase ISP a little bit.
So Wes, how long are we roughly looking at for a burn time?
We're looking at about 9 seconds.
9 seconds.
If everything goes well. That's for both propellants.
Can you see the liquid oxygen level?
I don't know.
We do not have
Nothing else.
view of the instrumentation.
Yeah, instrumentation's down. We're doing that bunker over there.
That were really more modern.
So I saw a question in the chat of, I have a question for the propulsion specialist. Why aren't you experimenting with electronically powered spacecraft propulsion? I've heard it's the future.
So
Hi, Alex. Hope all is well. So electric propulsion is really good for long duration space flight because it takes a long basically
It has
Let me
very
back
good fuel
up.
efficiency.
It has a very high ISP, but the thrust is very, very low. Like
On the order of millinewtons low.
yeah, like less than somebody like poking you with their finger. So it takes a very long time to accelerate a spacecraft to sort of a usable velocity to actually get somewhere with electric propulsion. So
It's great for deep space.
yeah,
Once
good
you're
for
already
deep
out of the
space.
gravitational field of the Earth, but to get to orbital velocity from the Earth, you're gonna need a lot more thrust.
Yeah, you need an impulsive engine. So you use that an impulsive engine, which is basically a chemical rocket for getting to orbit, and then also for orbit transfers between planets.
I see a hello in the chat. Hello, how are you? I also see something about a nuclear engine.
Yeah, nuclear engines would be awesome if they didn't.
So yeah, are we still LNG filling?
Yes.
Okay, we're still filling our liquid natural gas. And once that's done, we can proceed with the next step, which would be the ignition system installation. And then after that would be tank pressurization, and we can move towards the fire. George.
Hello, George.
At this time, I'd really like to thank anybody who sponsored the Rocket Project. Whether that's any previous members that were on the project, any current members who are on the project, any future members who are on the project. For instance, if you are an engineering student at UCI and you'd like to join the Rocket Project, we are actively recruiting. We'd love to get new members, and we'd love to hear from you. You can reach us on all sorts of social media. We have an Instagram, we have a Twitter, we have a LinkedIn page, we have a YouTube channel, as you guys can see. Or you could even just message one of the members directly, and they could put you to the right channels. But we'd also like to thank any technical staff who have helped us. Daryl has been a huge help.
Yep.
Derek Irwin has been a huge help.
And of course,
Professor Walter has been huge. Without a good advisor, it'd be really hard to pull something like this off. We're driving out into the desert to go test, and without someone there to kind of help guide us on right decisions to make from an engineering standpoint and also just from a team standpoint, it'd be really hard to pull something like that off. So, thank you, Professor Walter. You've been a huge help to the project.
And we wish you could have made it out here today. If I sit on 15, but then when I switch to 14, 14 is
Burn time. We're looking for about 9 seconds.
Yeah.
Best case scenario, 9 seconds. So far, we have about 3 seconds of usable thrust data from our very first static test fire, so we're looking to at least double that.
Guys getting closer?
Oh, we're up to 72 viewers. Awesome. Awesome. We're at about 8.6 pounds on our LNG tank.
Yeah.
On our LNG tank.
Well, Austin and I said to do 15, but to get Hanky wanted to up it to 20.
Yeah.
So we are at like
About a
Trey
third
said,
full.
like roughly 9 pounds of liquefied natural gas inside the tank, and our target goal is 20 pounds.
Yes, Dylan, it's liquid oxygen and methane.
So it's going to take perhaps another 5 to 10 minutes from here to
Proceed to the next steps, where we're going to do the ignition system installation. Yeah, so this is liquid oxygen and methane. We actually use natural gas because it's very, very close to methane, and it's incredibly difficult to source pure methane at a...
There's a rocky
yeah.
right there.
Yes, definitely. Yeah, anyone who's ever contributed to the UCI Rocket Project has been instrumental in making this happen. This isn't like a this year's kind of the work. This has been like years and years and years and years in the making. And we can kind of see our tanks in frame right now. You can see both of them, and the lines leading into the tanks from the tops are frosted over, and you guys can see the moisture in the air kind of collecting as frost onto the system.
Oh, thank God.
Are y'all running fuel rich the entire time? Are we, Wes?
Yes, we are running fuel rich the entire time. Yeah, we do fuel rich above the stoichiometric ratio because it reduces the combustion chamber temperature and it also increases ISP a little bit. And then towards the end of the 9 seconds, it'll become even more rich until the LOX tank is empty, and then it's solely burning natural gas outside of the engine.
Damn, our viewership's dropping. We're at 55 viewers right now. If you got anyone who likes rocket engines who you know of, shoot them the link. We hit 100 last time. You know, if we could hit even more this time, that would be awesome. We are not film cooling. We are ablatively cooling our combustion chamber. We have a phenolic tube in there that's basically going to absorb the vast majority of the heat being generated there. And kind of vaporize along with the fuel. Okay, so what does fuel rich mean? And so what you have a ratio of, well, I guess we should start with why do you have oxidizer and why do you have fuel in a rocket? So when you're flying in an aircraft engines use ambient air to burn their fuel, because when you need to combust fuel, you need an oxidizer of some kind to successfully ignite it. If you just have fuel, it won't burn, and if it does, it won't give you a whole lot of power out of it. So the idea is that you ignite an oxidizer and a fuel at the same time together. You mix them together, and then you ignite them, and that gives you combustion out the back end of the rocket engine. And so the fuel rich kind of comes from the ratio between the two of them. It depends on what propellants you use. There's some chemistry involved in, for instance, with methane, since it's CH4 and you have oxygen, there's I think it's a, what's it, H4, so it's going to be O8, so it's going to be 4 oxygen to each methane?
Basically, when you balance the combustion reaction, that'll give you a stoichiometric ratio of the propellants, which basically means you need X number of methane molecules combined with Y number of oxygen molecules so that you have a perfect ratio of combustion. So let's say it's, I don't actually know what ours is off the top of my head, but let's say it's like around 3 or 2.5. So that would mean like 3 oxygen molecules per methane. And so that's the stoichiometric ratio, and then fuel rich basically means just increase the amount of fuel above the stoichiometric ratio.
So typically you're looking at a mixture ratio of about 2.5 molecules of oxygen to methane, to anywhere up to 3.6 molecules of oxygen to methane. And you want to run fuel rich again just to keep temperatures down. Sending some SEDS UCSD folk. Awesome. So yeah, if you guys have any questions, feel free to pop them in the chat, and either a UCI Rocket Project member can answer it from the chat, or we can answer it on stream. What is the most dangerous stage of setting this bad boy up? That is a great question.
It is going to be a pressurization stage. So after we fill with propellants, they're at a pretty low pressure inside the tank, so it's not too volatile. They're in a pretty stable position. However, once we add roughly 500 pounds psi of nitrogen or helium to the tanks, then we get
Really high pressure tanks with
Yes.
really volatile propellants in there.
exactly. We're putting pretty high stress onto the engine at that, not on the engine, on the tanks at that point.
And on the entire fluid system assembly.
Exactly.
And so that's kind of why we do cold flow tests, we do pressurization tests, we do tests over and over and over again to kind of try to account for as many different possibilities as possible. We've got a small rocket on screen right now. I'm not sure whose rocket that is. Do you know, Corey? So I see a question in the chat asking if we're the only ones here with a liquid rocket. As far as I know of, we are.
Yeah.
Everything else that's flying today is a solid. What was the reason STF2 was scrubbed?
So STF2 basically it didn't fire because the oxygen, the main oxygen valve was at a higher pressure than was the design pressure, so it just failed to open.
It basically just had so much force pushing up against it that it wasn't able to open correctly. And that's why we ended up basically with a LNG burp almost.
Right.
Where we flowed out the LNG and we ignited it, but it only ignited with ambient air, so you didn't see proper ignition of the two propellants. Flamey end down indeed, pointy end up. So you can see we're back on the test stand now. You can see the ignition system is being installed inside of the engine. We have an igniter putty that we basically ignite, and that allows there to be a flame front inside the engine, so that way when we flow the propellants out, they're able to combust. Because otherwise, I mean, we can flow the propellants right out, and they just won't do anything. They'll just flow right out.
Because
so you gotta ignite
unfortunately, they're not hypergolic.
Yeah,
As Trey
unfortunately,
would
they're
like.
not hypergolic. As much as I would like to see us use hypergolic propellants, they're not. And so right now we're installing that igniter putty, and that step's important because if we flow the propellants out and the igniter putty is not correctly installed, it'll just shoot right out, and we'll just end up flowing out a bunch of fuel.
Mason wanted the laptop. Yeah. Ryan wanted it open.
I wanted to put it in the box.
You want to put it in the box, right?
Yeah, can I borrow your card?
So you can see now that the is that Hanky installing that?
Looks like Austin and
Not sure. Either way, our test stand crew is currently installing the igniter putty in right now. You can kind of see that, and it looks like they're good to go. So they're now walking away from the engine and just checking off all the other components on cold brew. But yeah, let's see if we can get up to 100 viewers. We're getting really close to ignition here. We're at 76. We're pretty close. So if, again, you guys know any other people on rocket projects who are interested, or anyone who's just interested in rocketry in general, shoot them the link. The more the merrier, you know, and pop down any questions you have in the chat.
Right now, our
Say that again.
we are very close to pressurizing our tanks at this current time.
We just finished igniter install, right?
Yes. So we have just installed our igniter, which is what we will use to light the engine once we flow propellants. As you may have seen, the truck drove away with our LNG doer. So the LNG tank is full, and we are preparing for pressurization.
Thank you, Rocket Powered Keith, for posting on the Bird app. We love to see more people on Twitter. The UCI Rocket Project also has a Twitter account if you guys are interested in following that. Hopefully we should have some pretty awesome shots of the test fire that we can kind of push out over time. You guys can see there's some tape over the engine. I'm not sure if that's to hold the igniter in or for something else. Yeah.
So are we live?
Yeah. We're live.
So that duct tape is gonna easily blow away from the thrust of our engine. So there's nothing to worry about too much.
What is your expected max thrust? We're hoping for like
About 940.
about 940
We're
pounds.
fingers crossed for over 1,000, but 940 is more accurate.
And for our impulse, we're looking for about 200 seconds. Specific impulse. Or no, impulse would be thrust over time, right? So that, or thrust times time. Sorry, specific impulse would be about 200 seconds, but looking about 900 times 9 seconds. So about 8,100 pounds, pound seconds of impulse. I might be wrong on that, but we'll get confirmation on that value right now. And so for now, we'd like to bring on another guest. We've got my fellow assistant propulsion lead, Sky Hargrove, on the line. Sky, why don't you introduce yourself? You might need to speak up a little bit because the mic's kind of far away from you.
Hello, my name is Sky Hargrove. Like Trey said, I'm also the assistant propulsion manager. Happy to be at the STF3 today.
So how long have you been on the project for, Sky?
I started last fall.
So a little over a year now.
Yep. About that, yeah.
And have you been involved in kind of the cold flow testing and working on cold brew during this testing campaign?
Yeah, we've been pretty busy in the lab, even though COVID restrictions. We've been being safe and getting the lab work done. We've had really good, solid results. We're excited to have a successful STF today.
What are you most excited about when it comes to Rocket Project or rockets in general?
I just think where we're going and the progress that we've made is really exciting, especially for a collegiate rocket team. And I think just coming onto the project as a sophomore and just how much I've learned is really amazing. We also have Zachy with us.
Yeah. So, how was it a large learning curve when you joined the Rocket Project?
I would say yes and no. There's still some stuff I don't know, but I'm learning from Austin and Jorge. I've really learned way more than I thought I ever would. Just even being a part of the cold flows and the testing. It's really amazing how much you learn just on the job. We've got some knowledgeable team members here.
Okay, we are very close to ignition. The system has been pressurized.
Oh, we have a confirmation on pressurization?
Yes.
All right,
so
cool.
The system has been pressurized and the test stand has been vacated. We are going to begin our go, no-go sequence, in which case
there's a series of checks that kind of let us know whether different portions of the test stand are ready on an individual basis, because we have thermocouples, pressure transducers, and electronic control over valves of all over the test cart basically. And so in doing that, we can kind of get an idea as to whether it's a procedure or whether we're proceeding or whether we're kind of looking back on some stuff.
So we just have received a full go for the hot fire. In a few seconds, we will ignite this engine.
So we have thrust is actually measured or calculated. So we have a measured or a calculated value that we have from the design and the design procedures, but we have a measured value from a load cell that's actually on the cart.
Okay, we just got the approval from FAR to go ahead and fire.
5, 4, 3, 2, 1.
There's ignition. So, as you can hear from the celebration all around me, we had a very successful engine test.
Good job, sir. Good job, sir. Good job.
That was very exciting. You could feel the ground shake as the engine.
Good job.
That's it.
Sir, good job. Good job. Good job.
That's what we like to see. That's what we like to see.
Thank you. Sorry, we'll be back in just a moment. So that is going to conclude our test fire. We're going to have a large high-power solid rocket launch in just a moment.
But in the meantime, we're waiting for a different rocket to fire first. And that one's not ours, is it?
No, the rocket that's about to fire is from the postgraduate naval academy, something like that.
Something along those lines. We're now going to be moving the camera over to the solid high power rocket. Again, thank you everyone who came out. That was sick. There were a lot of good mock diamonds on that ignition, and you could hear the reaction from everyone on the project. There's a lot that went into that, and thank you guys for showing up. It was awesome. That was really cool. You should be able to just rewind the stream if you'd like to see the ignition. If you just hit the back arrow on your computer, or yeah, just hit the back arrow on your phone or on your computer, you should be able to see it again. But that was incredible. And now we'll turn it over to this high power solid rocket that's on the stand over here. And you can see it in orange and white. All right, everybody. We're gonna be cutting the stream here in a moment, but we just want to thank everybody who came out. The air here is like absolutely electric right now. It's amazing. As shout out everybody who's on the project right now, who was on the project before, who will be on the project in the future. Anyone who's helped the project, Professor Walter, Derek, Daryl, you guys have all been a huge help. We couldn't have done it without you guys. Thank you to everybody who came to the stream. Thank you guys for supporting us. You know, STF1 was all right. STF2, you know, we didn't manage to get ignition, but this time this was awesome. You got to see mock diamonds. You got a really good long duration burn. It looked really stable, and we're really excited to kind of come up with the data and really see what the result of that is. I mean, I can't really put anything into really any eloquent words right now. I'm just so happy with how that turned out. It was amazing. There was just weeks and weeks of long hours leading into that, where people coming into the lab as much as possible, and this is just awesome to see this happen during COVID. And we just want to thank you guys so much for tuning in. Thank you guys for your support. Thank you guys for everyone who got hyped in the chat. You guys have been great, and we hope to see you guys around, whether it's at FAR or at other places. This has been awesome. Thank you guys so much.